Hello, in this video we study more applications of determinants. We will use determinant to find inverse matrices and apply determinant to solve system of linear equations. So we will learn the Cramer's rule and we'll see how determinants can be used to find area and volume. And finally, we will use determinant to write equations of lines and planes. Okay. Um, Before we start, I would like to remind you the case of 2 by 2 matrices. Okay, so suppose you have A equal to A, B, C, D, then we know that if A to negative 1 is X, then A to negative 1 is 1 over AD minus BC DA negative B negative C. Is that correct? Or that is nothing but 1 over determinant of A, and here you have D. D is what? D is C11, C21, C12, and C22. So if you remember that, Cij, this is cofactor, right, of the element Aij in the matrix A. Okay. So that is the case of 2 by 2 matrices. Okay. We have the following definition for n by n matrices. So if you have matrix A is Aij, where I and j is from 1 to n, right? Then the following matrix is called adjoint of A. That is what? That is C11, C12, and so on, C1n, C21, C22, and C2n, and so on, Cn1, Cn2, and so on, Cnn. So you take the transpose. This is the adjoint matrix of A. Okay. If you compare, this definition with the case of 2 by 2. With the case of 2 by 2. So basically you can rewrite this is 1 over determinant of A. And then here I write C11, C12, C21, C22 transpose. You see this? I just write transpose in here, and I just want to keep the order 1 1 1 2 1 3 and 1 n, because it is easier for me to memorize them. And then you just take the transpose. Such matrices are really important, and it turns out that the inverse of the matrix A, if X is equal to exactly the same line for 2 by 2 matrices. That is 1 over that A, or you can write here adjoint of A. Or sometimes just 1 over that A times adjoint of A. You see, is what we're having here. So that means in this case determinant can be used to find inverse. And of course, each time when you need to find Cij, you also need to calculate the determinant, right? There's no way to avoid determinant in this case. Let's consider the following example. We have matrix A is negative 1, 3, 2, 0, negative 2, 1, and 1, 0, and negative 2. The first question, we need to determine if A to negative 1 is X or not, right? Second one, find adjoint of A. Okay, this x. Is that correct? Of course, it exists does not depend, and it does not depend on the invertibility of the matrix. I just want to mention that, okay? Because sometimes we say, yeah, let's find a to negative 1 if exists, but the adjoint of a matrix always exists, okay? So C, find the inverse of A if exists. Okay, at this moment we know two methods how to determine if the inverse exists or not. The first method is to use row elementary operations to check, right? If in the row echelon form of the matrix has all non-zero rows or not. If all rows are non-zero, so the inverse exists. Okay, or you can use determinant to check. If the determinant is not zero, then A is invertible. So let's use the determinant because we are in this topic, right? And of course, determinant is easier to find and shorter to do. So let's find determinant of A. Determinant of A is negative 1, 3, 2, 0, negative 2, 1, and then I add the first to the third because I want to make this guy 0. Add 3 in here and 0 in here. Each time when I add some row to another, I don't change the determinant, right? And this is equal to negative 1 because we have negative 1 in here times determinant of negative 2, 1, 3, 0. This is the minor I got after deleting the first row and the first column. So the determinant is equal to negative 1 times negative 3, which is 3, not 0. Perfect. A is invertible. All right. Let's find that joint matrix of A, and then we use that joint to find the inverse. Okay. That joint of A is, let me copy the formula again, right? 1, 1, C1, 2, C1, 3, C2, 1, C2, 2, C2, 3, C3, 1, C3, 2, C3, 3, and don't forget to take the transpose, okay? Okay, let me copy the matrix in here, okay? So that we can see that each time I have negative 1, 3, 2, 0, negative 2, 1, 1, 0, and negative 2. So from here I have C11 is what? C11 is, plus determinant of negative 2, 1, 0, negative 2, which is 4. I write plus in here because, here the position is 1, 1. You see? And then let's say C1, 2. So I have negative, okay, because the position is 1, 2. 1 and 2 are not of the same parity. So I delete the first row and the second column. I have 0, 1, 1, negative 2. Determinant of 0, 1, 1, negative 2. This is negative, negative 1, and that is 1. Okay. Then I can find C13. Okay, let's find C13. C13 is plus because 1 and 3 are of the same parity. So I delete the first row and the third column. Okay, I have determinant of 0, negative 2, 1, and 0. This is 2. Okay. Then I have C14. Again, this is with the negative determinant. Oh, no, not C14. Sorry, C21 because we finished the first row. Okay, with the negative. And I delete the second row and the first column. I still have 3, 2, 0, and negative 2. So this is just 6, right? And then let's find C22 is plus. In here I have negative 1, 2, 1, negative 2. Okay, so you get 0. And then C to 3 with the negative in here, and I have negative 1 3 1 0, which is 3. Okay, I move to the next row, C 3 1 plus, then I have negative, not negative 1, 3 2 negative 2 1, right? That is 7. I have C 3 2 with the negative 3 2, so I delete the third row and the second column. I have negative 1 and 2 in here, and then 0 1, I have 1. Okay, and the last one is C 3 3 positive 3 3, I have negative 1 in here, 3 0 and negative 2. All right, so this is equal to 2. All right, I have all cofactors in here, 4 1 2 6 0 3 7 1 and 2. Now let's fulfill this matrix. Okay, C11 is 2, no, 4 1 2 6 0 3 7 1 and 2, and take the transpose. All this is equal to 4 1 2 6 0 3 and 7 1 2. Because you rewrite, rows in the matrix as columns in the transpose. Okay, and that is the adjoint of A. Then, since we have the adjoint of A, write this, right? You can write the inverse of A. Okay, so I just copy this right here, and then I write the inverse of A to negative 1 equal to 1 determinant of A times the adjoint. Then what is that? The determinant is, let me see, we already calculated, that is 3, right? So I have 1/3, 4 6 7 1 0 1 2 3 2, and that is, now you can bring 1/3 into the matrix, 2 7 over 3, 1/3 0 1/3 2/3 1 and 2/3, and that is the inverse of A. So you can see actually in this case we avoid a lot of computations. Why? Because you have fraction in here. I bet if you have fractions in here, if you use row elementary operations, we have to do with a lot of computations with fractions. So this method helps us to avoid such computation. Okay. Now let's talk about another application of determinants, Cramer's rule. Suppose that you have the system like on your screen. Okay, I have A1, A12, and A1J. So I just mention the J column in here, the J column, and the coefficient matrix is of course n by n, and that coefficient matrix is invertible. Okay, so that means the system has a unique solution. Okay, a unique solution. So we need to find the solution. Of course, we know how to do that already, but with determinants we can find the solution in a direct way. How? The Cramer's rule says if you replace the J column, right, by the free coefficient column, you have a matrix AJ. Okay, let's say A is the coefficient matrix, and from A you replace the J column by B, B1, B2, and so on, Bn. then the xj is equal to determinant of aj divided by determinant of a. Means where aj is what? Aj is, you get the matrix, by replacing the jth column in a, by the free coefficient. Yes, by the free coefficient column. Okay, so if you move the j from 1 to n, of course you have the solution x1, x2, and xn. Okay, let's demonstrate how this method works for 2 by 2 matrix. Okay, and then we move to 3 by 3. Oh, I think we can do for 3 by 3 right away. Okay, so let's solve the following system: -1, 2, -3 in here. I have 1. The second is 2, 0, 1, 0, and 3, -4, 4, and 2. So the matrix A is -1, 2, -3, 2, 0, 1, 3, -4, and 4. I can write A1, A2, A3 because, we have 3 variables, right? This is for x1, this is for x2, and this is for x3. Then you have A1 is equal to, you just need to replace the first column by the B, 1, 0, 2, right? So I write 1, 0, 2 in here, 2, 0, -4, -3, 1, and 4, okay? And I have A2. You just replace the second column, okay? So I have -1, 2, 3. The second column will be the B, 0, 2, and then -3, 1, and 4, and A3. You have -1, 2, 3, 2, 0, -4, and 1, 0, 0, 2. And now we need to find determinant of A1, determinant of A2, and determinant of A3. And then you divide by determinant of A, and you get the solution, okay? But let's find determinant of A. So we have 3 by 3 matrix with 1, 0. I can, but I want to make one more 0. By multiplying the third row, the third column, by negative, or you might just multiply the first row by 2 and add to the third. Let's do that. Then that is determinant of -1, 2, -3 in here. I have 2, 0, and 1, so I get I have 1 in here, 0 in here, and -2. Okay. This is equal to 2, but the position of 2 is 1, 2. So we have negative, right? -1 in here. Multiply by 2, 1, 1, -2. You have -2. And then inside you have -4 minus 1. So that is 10. The determinant of A is 10. Okay. I just keep writing here. 10. So now let's find the determinant of A1, A2, and A3. For A1, this is very good because you have 2 zeros in the second row. So that of A1 is equal to, the position of 1 is 2, 3. So you have negative, right? And then 1, 2, 2, -4. And that is 4 minus 4 is -8. -8 with negative is 8. Okay. And then you have determinant of A2. So we have 1, 0 in here. I can, but now I just want to do the diagonal method. So I have -1, 0, 4, which is 0, and then 1, 1, and 3. So I have 3. And then 2 with 2 and -3 is -12. Okay. With the other diagonal, I have 0. Okay. This guy will be 0. 1, 2, and 1 is -2. With negative is +2. And then 2, 1 with the 4 is A with the negative. So I will have 9, 10, so 20, so I have negative 15, okay? All right, let's move to this one. We'll have 2 right here with 2 zeros. Perfect, so I can do negative 2, negative because the position is 2, 1, right? And then we have 2, 1, negative 4, and 2. So you have negative 2 inside, you have 4 plus 4, which is negative 16, okay? You have all determinant uniques, right? So x1 equal to 8 over 10, which is 4 over 5. From here I get x2 equal to negative 15 over 10, which is negative 3 over 2, yes. And here you have x3 equal to negative 16 over 10, which is negative 8 over 5. And that is your solution. Okay, so basically, you know, in the Cramer's rule, you need to find determinants, and it depends on, you know, the method you use. Maybe the diagonal method is faster. Maybe, you know, the cofactor method is faster. But you know, that is your choice. Right. Let's talk about area, volume, and equations of lines and planes using determinant. So suppose that on the plane you have 3 points, A and B and C. Okay, this is A, this is B, this is C, with coordinates x1, y1, x2, y2, and x3, y3. Then you can find area of triangle ABC using determinant, that is plus minus 1/2 x1. In the first column you have the x coordinate. In the second column, you have the y coordinate, and in the last column, you have 1. Okay, we have plus minus in here because in case, you know, we may choose the positive because, you know, determinant may be positive, right? May be negative. If the determinant is positive, so we choose plus in here. But if determinant is negative, we choose negative so that we have a positive area. Agree? You know, this formula can be proved easily, so you can read in the textbook. Let's consider the following example. I have 3 points, A 1 1, B 2 2, and C 4 3. So I need to find the area of this, right? Triangle. The area of ABC equal to, I write 1/2 plus minus in here. Determinant, in the first I have 1, 2, and 4. You know, I write in this form so that, you know, you will not forget about the x coordinate. We just collect all 1, 2, and 4. And then the second column will be the y coordinate, 1, 2, 3. The last column is 1, 1, and 1. And our job is to evaluate this determinant. Okay. So I will use diagonal method. So I have the main diagonal right here would be 1 times 2 times 1, and then the second one is 1 times 1 times 4 in here, and then the last one is 2 times 3 times 1. All these 3 terms with positive signs. Once I finish, I move to the other diagonal, right? But with the negative side, I have 4 times 1 times 2 times 1 minus 2, 1 with the 1 right here. So I have 2, 1, and 1, and then minus 3 times 1 times 1. Okay, let's simplify that and we get what we need. Okay, so I have 1, 2, 1 in here, 1, 2, 1 in here. That will be cancelled out. And then I have 2, I have 6 in here, I have 4 in here, 3 in here, 8. So basically we have negative 1, right? The determinant is negative 1. Okay, don't forget we still have times plus minus 1/2 in here. Sorry, I mixed this term, right? So I have plus minus 1/2 in here. I have 4 plus 6 minus 8 minus 3. So that is 1/2. Okay, of course you pick this guy is -1, but you pick a -1/2, so the area is 1/2. All right, look at this. So what happens if 3 points A, B, C are collinear? What does mean collinear? Collinear means, A, B, C are on the same straight line. In that case, the area is 0. Is that correct? So if you have A, you have another B, and you have C, they are collinear, then the area is, let's say the area of ABC is 0. That means the determinant is 0, right? The det is 0. The det in the formula right here. The det is 0. So from this observation, you can find the equation of a straight line if 2 points are given. Okay? How? Suppose that you have 2 points, A, x1, y1, and B, x2, y2, right? You need to write the equation of this straight line. That means you need to describe all points C, x, y, such that A, B, C are collinear. Is it correct? So the determinant is 0, means you have x1, x2, and x, y1, y2, and y. 1, 1, and 1 is 0. You see, instead of x3 and y3, so you just write x and y, because you need to describe all points x, y, right? Such that, A and B and C are collinear. So, you just put the determinant equal to 0. And solving this, you have the equation of a straight line. I think it's pretty easy. Let's consider the following example. You just pick the point 2, 4, and then another one is -1 and 3. So the equation star will be 2, -1x, and then y1 is 4, 3, and y 1, 1, and 1 in here, you get 0. Okay, so we need to find coefficient of x and y. So that means I would like to expand the determinant along the third row. So I have this is 3, 1, that is 3, 2, right? So for 3, 1 I have x, determinant of 4, 1, 3, 1 minus y, because the position is 3, 2. Okay, and here I have 2, 1, -1 and 1, and the last one is 1 with the plus, 2, 4, -1, and 3. This equals to 0. Then I have, the first coefficient is x times 1 minus y times what? 2 plus 1 is 3. And then the last one is 10, right? 6 minus plus 4 is equal to 0. So the equation is x minus y plus 10 equal to 0. You see, it's pretty easy, right? The last application of determinants we consider today is volume of tetrahedron. Okay, so suppose that we have 4 points in the space. In the previous example, we studied 3 points in the plane, and now we have 4 points in the space. x1, y1, z1, x2, y2, z2, x3, y3, z3, and x4, y4, z4. And we need to find the volume of this tetrahedron. Okay, that volume can be found using this formula. Here you have plus minus 1, 6, right? Again, plus minus just says about the sign. If the determinant is negative, so you pick plus. Negative, sorry. If the determinant is positive, so you pick positive. And again, right, in the first column you have the x coordinate, right, of all points, and here you have the y coordinate of all points, and here you have the z coordinate of all points. The last column is just ones. Okay, again, if 4 points are coplanar, then they lie on the same plane. That means the volume is zero. So you just have the determinant equal to zero. And that observation helps you to write an equation of a plane passing through 3 points. Does that make sense? So, in order to do that, you just replace, one x4, y4, z4 as x, y, and z. And you just write out the determinant and get the equation of the plane. Okay, so we just solved one problem, find the volume of some tetrahedron, and about the equation of the plane. I think you can do that in homework. All right, let's consider the following example. We have 4 points. A is 0, 1, 0, B -1, 3, 2, C is -2, 0, and 1, and D -1, 1, and 1. Okay, so let's find the volume of this tetrahedron. I have plus minus 6, 1, 6, and then I plug all coordinates into the determinant. I have 0, -1, -2, -1. The next one is 1, 3, 0, 1. The next one is 0, 2, 1, and 1. The last column is 1, 1, 1, and 1. Okay, so you can see in the first row we have 2 zeros, right? Let's make one more 0 by multiply the last column by -1, add to the second. So you have the following one, plus minus 1, 6, okay? And here I have 0, 0, 0. I have 1, 1, 1, 1. The first column is still the same, -1. And here I have 2, 1, and 1. Here I have 2, I have -1, and I have 0 in here, okay? So we have 3, 0. I can delete the first row and the fourth column, but the position of this guy is 1/4, right? So I have negative, but you see we have plus minus in here, so we are okay, right? So I write plus minus 1, 6, determinant of -1, 2, 2. And here I have -2, -1, 1, -1, 0, and 1. Okay, if you want, you can make more zeros. So let's do that. Plus minus 1, 6. I multiply the first row with -2, add to the second, and the first row by -1, add to the third. So I have -1, 2, 2 in here, 0 in here, -2, I have -5, -2, I have -3, 0 in here, I have -2, and -1 right here. Perfect. Again, right, we erase the first row and the first column. This equals to plus minus 1, 6, -5, -3, -2, -1. That is plus minus 1, 6, and then I have 5 minus 6. Overall, you have 1, 6. Okay, so that is the volume of our tetrahedron. Okay, so I think that is all about applications of determinants in this course. So we finished chapter 3 right here. Thank you.